Thank you for your introduction. So recently, when I say next generation high-density magnetic recording, many people say that there's no next generation magnetic recording because the hard disk industry is having problems. But I trust by overcoming various challenges of material issues, I trust that we will be having next generation high-density magnetic recording. So I will be talking about media and lead sensors using various materials. So this is the roadmap published by ASTC. ASTC is a research consortium invented by the recording industry. And this is the areal density of recording, and this is the year to be developed. And currently, the areal density of hard disk drive is below 1 terabit per square inch. And in order to sustain the industrial development, it is necessary to keep increasing the areal density. And the future target is about 2 terabit per square inch, around here. So in order to reach this area, with the current recording system, we won't be able to reach this goal. So the issues are currently we use perpendicular magnetic recording method, and for the media we use cobalt-based alloys. So cobalt-based alloy, its magnetocrystalline anisotropy energy density is about 0.3 megajoule per cubic meter. And we have to satisfy this condition. The magnetocrystalline anisotropy energy has to be 60 times larger than the thermal energy. Otherwise, the stored data will be completely disappear. And from this, if we calculate the paramagnetic limit of the ferromagnetic material, with the cobalt-based alloy, this will be about 11 nanometer. And this is the area that is required to achieve 1 terabit per square inch. And as you can see, there are only 4 or 5 particles. And in order to keep sufficient signal-to-noise ratio, we need at least 8 particles in this area. That means we have to substantially reduce the particle size. But with the cobalt-based alloys, we won't be able to do that. And as to the reason, currently, the magnetic tunneling junction, MgO-based magnetic tunneling junction is used. And depending on the relative orientation of the magnetization, resistance changes. So this is the current magnetic sensor being used for the lead sensor. But in order to go to this area, we need to move to a totally different system. And one proposed and most promising method is known as heat-assisted magnetic recording. And in this system, instead of using cobalt-based alloy, we use L10-based iron platinum because its magnetocrystalline anisotropy energy density is 7 megajoule per cubic meter, more than 10 times larger than that of copper-based alloy. And based on this, we can calculate the paramagnetic limit. That will be 2.5 nanometer. That means we can reduce the grain size to 2.5 nanometer, but we can still keep the ferromagnetic. But when we make such a fine grain size, as you know, from the Stoner-Wolfers curve, the porosity will increase very much. And we cannot write with the stray field that we can obtain from the right hand. So in order to overcome, we irradiate laser and heat up this part, then the porosity increase. And at that moment, we can apply the field about 1 Tesla, and we can write to the medium. So this is called heat-assisted magnetic recording. And another issue is the lead sensor. And in order to use for high-density recording, we have to use a device which has a much lower device resistance. So TMR device will be replaced with some other magnetic sensor. And what we believe most promising is current perpendicular to plane giant magnetoresistive devices. So today, in today's talk, I will be covering the materials issues for these two subjects. So first, let me start from what is the problem of making a recording media using iron platinum. And this is a phase diagram of iron platinum. And if you bring a bulk iron platinum alloy and heat up the temperature of 1,300 degrees Celsius, then if you cool down, this is all the disorder in temperature. So A1 disordered iron platinum will order to the L10 structure. So you get very high magnetocrystalline anisotropy material. But in order to use this as a media, we have to use sputtering method. Then this one bypass disorder in temperature. At room temperature, we make thin film, and most of the case, they are disorder. Then we have to make this metastable disorder phase to the stable L10 phase. And in order for phase transformation to occur, we have to increase the temperature so that atomic diffusion occur. That temperature is about 300 to 600 degrees Celsius. Then, of course, we can make this order to L10 structure, as you can see from the diffraction pattern. But at the same time, this particle cosmic occur. So because of this, we cannot maintain the nano-granular structure. So this was the difficulty, was making iron platinum media structure using iron platinum. So one solution we thought about is starting from amorphous substrate and sputter deposit, MgO underlayer. So MgO has a strong tendency to show 001 orientation in polycrystalline state, and this is the TM image of the MgO underlayer. You see a lot of small crystals. And once we can align the MgO to the 001 texture, then we can grow iron platinum on the 001 structure. And what we do is we grow iron platinum while the substrate is heated. Then by the surface diffusion, they order to L10. And instead of using only the iron platinum, we mix with iron platinum and carbon. And carbon has a very strong tendency to phase separate with iron platinum. So during the growth, they phase separate, and we can obtain a very nice isolated granular structure with a very small size distribution. And since 001 orientation is strongly textured to the normal perpendicular to the plane, they show strong perpendicular anisotropy. And this is a cross-sectional image. They always have a heptatextual relationship. And we published this result in 2008, but at that time the coercivity was too low. So what we have done is alloy with silver and grow such a media with the same method on top of silicon oxide, MgO underlayer, and iron platinum carbon. And we get a nice granular structure with very high coercivity. And when we presented this, scientists at HGST got interested in, and they tested this media with heat-assisted magnetic recording. And this was in 2011, but at that time, they were able to demonstrate 550 gigabit per square inch recording is possible to this media. So this was stimulated industry that iron platinum carbon can be a real media. And then later on, we studied how silver works. And during the growth, silver appeared to be rejected from the core part of the particle. And this one enhanced the kinetics for the L10 ordering. And we have core shell structure, and this leads to the high coercivity. And But after that, ASTC studied what is the specification for 2 terabit per square inch recording and 4 terabit per square inch recording. And for the time being, we don't have to worry about 4 terabit per square inch because it's too far. So let's look at the requirement for the 2 terabit per square inch. And these are the highlight of the specification. The diameter of the grid should be around 6 nanometer, and the center to center pitch distance should be around 7. And size distribution should be less than 10%, and the aspect ratio have to be 1.3. They have to be columnar, right? And the total thickness should be thicker than 9 nanometer. And the important thing is easy access distribution has to be smaller than 2 degrees, and surface roughness has to be sufficiently small. So the early iron pattern carbon media didn't satisfy this condition. One of the difficulty was up to 6 nanometer, we can grow iron platinum nicely. But if we try to make this, for example, 10 nanometer, as I mentioned, iron platinum carbon has a very strong tendency for phase separation. So first surface is coated with carbon, and second layer of iron platinum growth. And in this case, we don't have MgO seed layer, so these grains are totally randomly oriented. So because of this, we lose anisotropy in thick iron platinum carbon film. So in order to overcome this difficulty, this was a very difficult problem. We had to spend a lot of time to overcome. And one idea we got is why don't we change the chemical composition of carbon, starting from high carbon concentration, and we introduce high number density of nuclear, and thereafter to suppress the phase separation, reduce the carbon concentration. And in order to suppress the coarsening, we again increase the carbon concentration. So by this way, we were able to tune the microstructure of the iron platinum carbon media. And this is the microstructure of the 6 nanometer film. Up to 6 nanometer, you do not see any difference. This is coarse sputtered film, and this is compositionally graded sputtered film, and they look the same. So this one does not make any difference. If the thickness is 6 nanometer, if 6 nanometer thickness is okay, these do not make any difference. But if we try to make them to 10 nanometer, in the case of coarse sputtering, we get really messy microstructure. The reason is, as I said, carbon segregated on the surface, and on top of that, the second layer is grown. So because of this, we lose the columnar mass. But when we carefully control the carbon concentration, we can keep the columnar shape to up to 10 nanometer. At the same time, we can get the very nice in-plane granular separation. So by this way, in this case, we lose perpendicular anisotropy, but by doing this, we can obtain very nice perpendicular anisotropy with a small in-plane component. So we can further tune the microstructure, and currently we can attain 6 nanometer pitch distance, 8.6 nanometer. And if the aspect ratio can go to 1.9, although if we try to make this thicker, we tend to get the in-plane component. But this one shows iron platinum carbon media is ready for 2 terabit per square inch record, heat assisted record. So now, then we have to think about the reader. So this is the hard disk drive, and here's the head. And for the lead sensor, currently, tunneling magnetoresistive devices are used. So this is iron copper boron, MgO iron copper boron, and this was invented by Dr. Yuasa's group at AIST. The problem is, since we have to use MgO, the device resistance is very large because the conductance occurs by the tunneling. But for the 2 Tbit per square inch recording, there is a requirement. We need lower device resistance and high MR ratio. And this is the MR ratio and RA value for all types of magnetoresistive devices. So when we use MgO as a barrier, if we try to reduce the thickness, reduce the resistance, then MR ratio decreases. So no MR devices can satisfy this condition for 2 Tbit per square inch recording. So important thing is we have to reduce device resistance without degrading the MR ratio. So the one thing we thought is why don't we use a metallic layer instead of insulator? And this is called giant magnetoresistance since the current is applied perpendicular to the plane. This type of device is called the current perpendicular to plane giant magnetoresistive devices. So depending on the orientation, resistance change, but this has been known, but the question is how to improve the MR ratio, because the typical MR ratio for CPP-GMR using standard ferromagnetic layer is like 5% or so, very small value. So we can use them as a sensor, so we have to enhance the MR output. But if we use material with high spin polarization, one typical example is copper-based Heusler alloy, whose band structure is known to show half metallicity, where there's no, the conduction electron is 100% spin polarized. If we use such a material, we may be able to enhance the MR output. So let's look at, compare the two types of magnetoresistive devices. The principles are saying if they are anti-parallel, electrons are more scattered. If they are parallel, electrons are less scattered, so the resistance becomes low compared to the anti-parallel configuration. And in the case of tunneling magnetoresistance, according to the Juliet equation, TMR should follow this equation. And P1 and P2 means the spin polarization of the tunneling current, not the spin polarization of the material itself. So if we use the material which provides 100% spin polarization, we should be able to get very large TMR values. In the case of giant magnetoresistive devices, the MR output is given by these two terms, and this is called the bulk scattering term, and beta corresponds to the spin polarization of the current, and gamma stands for the spin polarization, spin asymmetry of the interns. So if you look at this, you may wonder why TMR gives such a high MR ratio, because this is an example of MgO ion magnetic tunneling junction, TMR device, and spin polarization of ion is only 0.4%. Nevertheless, this one gives large MR ratio. This is because MgO has a spin filtering effect. This one preferentially gives large conductance for the specific electron type. So if we look at only the delta 1 band electron, this one shows half metallicity. So in the case of MgO-based MPJ, we do not have to worry about the spin polarization of material itself. But in the case of CPP-GMR, we do have to worry about the spin polarization of the material itself, because MR output is given by these two terms, and one is bulk term and another is interfacial term. And in order to enhance beta, the solution is to use half metallic material. And typical example is copper-based Heusler. And this is the definition of the beta, and this is spin polarization of the current in the material. And another term is interface spin asymmetry. How much spin asymmetry or spin polarization we can get at the interface. And there is a theoretical study by this work, and based on this, the matching between silver and Heusler alloy appears to be very good. And if we select the combination of ferromagnetic and non-ferromagnetic layer, we can get large spin asymmetry at the interface. So if we select a materials combination, we should be able to enhance MR ratio substantially. So in order to do that, we have to search for what kind of material is suitable for this kind of application. So in our case, starting from the published band structure calculation, the half metallic material shows band gap in the minority electron, and make bulk alloys and measure X-ray. Based on this diffraction, we can determine structure, whether or not they are B2 or L1. And also by measuring thermal analysis, we can determine Curie temperature. And Curie temperature has to be substantially higher than the room temperature for the application. And some alloys shows all the disordering temperature about below the melting point. And good Heusler alloy for suitable for application shouldn't show the order disordering transformation below melting temperature, because in this case, the L1 structure is stable up to melting temperature. That means they are compound rather than order disordering system. So by making various alloy with using point contact and reflection, we can estimate the spin polarization at 4 Kelvin. But we cannot measure the spin polarization at room temperature. But by doing this, we made various ternary Heusler alloys and quaternary Heusler alloys. And we found that the spin polarization of ternary Heusler alloy ranges from 50 to 60%, not that high as we expected from the theoretical prediction of half metallicity. The reason would be many ternary Heusler alloys, their film level is near the edge of the band gap. So because of this, if we have some disorder in the Heusler structure, we cannot obtain 100% spin polarization. But by making quaternary alloy, we can tune the film level, and sometimes we can bring the film level to the center of the band gap. In such a case, we observe higher spin polarization, and some of the selected alloys shows spin polarization close to 70%. So we thought that these materials must be pretty promising. So based on this, we made such a simple device, epitaxial device, and starting from 001 MgO single crystalline substrate, we deposit thin chromium for improving bonding. And then silver, this is very important to enhance the L2 ordering of Heusler alloy. Thereafter, we put the thin spacer of 5 nanometer, then deposit the Heusler alloys again. So here the Heusler alloy we use is cobalt, iron, gallium, germanium. This is our favorite alloy. We found this alloy is pretty promising. And after making this, we anneal these devices and measure the MR output. The important thing is the theory predicts this is a half metal with perfect L2 modeling. Heusler alloy can be half metallic. But when we prepare these films by sputtering, in their sputtered condition, they become A2 disorder, BCC phase. And after that, we have to anneal them so that they become L2 structure. But toward this direction, first we get B2 structure most of the case. And thereafter, if thermodynamical condition is met, some of them go to L1 structure. So after making such a simple tri-layer structure, we measure the CPP-GMR, and that one gives only 1.5 milliohm square micron, very low value. But as we increase the annealing temperature of the device, this one increases because BCC phase become B2 order, and accompanied by that, the spin polarization increase. And after that, if we anneal this at 600 degrees Celsius, this one reached 12 milliohm square micron, which was at that time the largest value that we can obtain from the CPP-GMR. And when we look at the cross-sectional image, we can see that this ferromagnetic layer shows L1 structure. So because of the enhanced spin polarization by the ordering to the L1 structure, we believe that the MR output has been enhanced. So even if I show the MR values using delta array value, not many people can understand how much it is. So here's the MR ratio converted from delta array values. So that device gives at 300 room temperature 57% of MR ratio. So this value is extraordinarily high for CPP-GMR because earlier highest value was around 10%, 6 times larger than the CPP-GMR value using standard ferromagnetic layers. And another interesting thing is when we decrease the measurement temperature, for example, to 10 Kelvin, this MR ratio is enhanced to 183%. As higher than we can obtain from the many not good, very good TMR devices. So if we plot the delta array value as function of temperature, we found that compared to the low temperature value, room temperature value is 1/3. So somehow this MR is substantially degraded when we use it at room temperature. So what is the reason for that? In order to understand the reason, we made a plot, we measure delta array value as function of the thickness of the ferromagnetic layer. Then we can see this kind of change. And fitting this experimental data to the Barrett-Feld equation, we can deduce beta and gamma. This is bulk spin polarization, and gamma is interface spin asymmetry, and for 2 temperatures. So at the 10 Kelvin, we found beta is 0.93, 93%. This means this alloy is essentially half metal. And the gamma value is also very large. And when we go to room temperature, beta slightly degraded to 0.83, and gamma is substantially decreased to 0.6. So in order to improve this, we have to understand what is the reason for the large degradation of MR. So we measure first we measure the magnetization value, bulk magnetization value. And this one does not change even if we go from cryogenic temperature to room temperature. But when we look at the change of the MR output, this one shows large degradation, although the magnetization itself doesn't change. So what is the reason for this? Based on this, we can say that this is bulk value, bulk contribution. The majority of the reason for the large degradation toward room temperature is the interface. We believe that at the interface there is a termination of ferromagnetic layer, and this one becomes thermally unstable, so we cannot keep high spin polarization at the interface. So for application, the room temperature behavior is most important, and we deduce the spin polarization at low temperature, but estimation of spin polarization at room temperature or temperature change is very difficult. So one thing we did is Professor Hono recently published a nice paper, and according to him, anisotropy magnetoresistance, the difference of the resistance when it is measured parallel to magnetization, and when it is measured perpendicular to the magnetization, then we can measure anisotropy magnetoresistance. And according to this theory, this anisotropy magnetoresistance has a correlation with the difference of the difference of the band density of state for the upspin and downspin electron, and the difference of the conductance for the upspin and downspin electron. So we should be able to correlate anisotropy magnetoresistance with spin polarization somehow. Even if we cannot measure, we can correlate. So let's see how they are correlated. So this is the delta array value for the CPP-GMR with different Heusler alloys. So this is delta array for the cobalt, manganese, gallium, germanium, and this is AMR value. They show very good matching. When I saw this data, I said it's too nice to believe. But when we measure different system, for example, cobalt, iron, gallium, germanium, this one again shows excellent correlation. So when we correlate delta array and AMR ratio, they show very good matching. So based on this, we can say that measurement of anisotropy magnetoresistance could be a very good fingerprint to estimate how spin polarization changes as function of the temperature. So this is Sakuraba-san's work, and here's the Fermi level of various Heusler alloys, and this is the band gap. And when the film level is close to the band gap edge, then this anisotropy magnetoresistance, normalized anisotropy magnetoresistance, shows large temperature dependence. That means the bulk spin polarization is substantially degraded at the room temperature. But when we look at, for example, cobalt, iron, germanium, gallium, its film level is in the center of the band gap. These materials do not show much dependence on temperature. Even if we go to room temperature, the bulk spin polarization does not appear to decrease. So in order to keep high magnetoresistance using this material, we have to somehow improve the interface, particularly improve the thermal stability of the magnetization of the interface. So how can you improve the CPP-GMR output? There is a very nice paper published in 2009. This was published by the scientist Seagate, and they did the original work on the Heusler alloy-based CPP-GMR. And when they select the spacer, they proposed that Heusler alloy non-ferromagnetic spacer could be very good, because the band structure will be very similar. That means for the majority electron, their conductance will be large. But for the minority electron, their conductance will be very small. That means the gamma will be substantially improved. But somehow, after the publication of this paper, not many experimental work. So we decided to try this, and cobalt, iron, gallium, germanium, our favorite Heusler alloy. Even if we anneal them, most of the case they end up with the P2 structure instead of going to L10 structure. So when we look at the phase diagram, copper, zinc, and silver zinc has a P2 compound. So we thought it might be interesting to make copper zinc or silver zinc as a spacer, because then after annealing we can get all the P2 structure GMR. In this case, because of good band matching, we may be able to get large amount of output. So based on this, we prepared CPP-GMR. This is earlier result. Cobalt iron gallium germanium with silver spacer. And we changed the spacer to copper zinc and silver zinc. And after making a simple tri-layer structure, we anneal them, then the MR output increased. And in the case of copper zinc, we get larger MR output. Good merit is even for low temperature annealing, we get high MR output. But when we select silver zinc, this MR output keep increasing, and by annealing at 650, this MR output becomes almost 2 times larger than the earlier world record. So we got very excited. We thought that the concept of band structure worked, and the MR ratio was 60%. So we look at the structure using TM, and this is the cross-sectional TM of the device, annealed at 350. And this is cobalt iron, gallium, germanium, silver zinc, cobalt iron, germanium. And as we expect, we see zinc signal from this silver zinc layer, and these are cobalt signals. But we get very large MR output when it was annealed at 630 degrees Celsius. So we look at the cross-sectional image, and silver spacer is here, but to our surprise, zinc disappeared. So some zinc remains at this CFGG silver interface, but the zinc in silver zinc just vaporized and disappeared. So turned out to be this is a CFGG, silver CFGG, CPP-GMR. Nothing special. Nothing to do with the band matching. So we look at the structure in the as deposited condition we get. This is a CFGG was B2, silver zinc was B2, and CFGG was B2. So all B2 CPP-GMR. And when we anneal this at 350, to our surprise, this silver zinc changed to the FCC structure. Silver zinc is initially B2, so it's BCC based, but this one changed to FCC structure. And after annealing at 630, this one becomes pure silver with the FCC structure. So this turned out to be CFGG, silver CFGG, CPP-GMR. So the reason why we got high 2 times larger CPP MR output is during zinc vaporization, zinc have to diffusing. So this one enhanced the kinetics for the L10 modeling, just like silver in iron particle. So nothing to do with the band matching. So we were pretty much disappointed with the result, but we thought it worked, so it's okay. But we wanted to test the band matching concept. So we selected this time nickel aluminum, which is very stable B2 compound, which is used for the high temperature application as well. So their lattice matching is very good, and this is if this is B2 order, they have the same structure. And we asked theoretician Professor Mueller to calculate the conductance of the electron. It turned out that nickel aluminum compared to silver, silver has the most widely used spacer materials with Heusler ion. But nickel aluminum shows much better band matching. The conductance of the majority electron becomes larger. So we thought nickel aluminum should be good, but there is a problem. If we use nickel aluminum as a spacer, when we increase the thickness of the spacer, MR output decreases. So this result was taken from the PhD thesis of my former graduate student. The reason why you can find this data only in his thesis is we tried to publish this paper and submit it to 2 journals. In both cases, it was rejected. So we gave up publication, and you can find this data only in his thesis. But this one shows the reason why MR decreases when we increase the spacer thickness is because the spin diffusion length of nickel aluminum is very short. We estimate around 8.1 nanometer, 8 nanometer. So if we use such material as a spacer, we won't be able to achieve high MR output. So we thought, why don't we put nickel aluminum only at the interface and use silver with long spin diffusion length as a spacer? Then this is the result. We put nickel aluminum between silver and CFGG, and as function of thickness, we get peak MR ratio at 0.2 nanometer nickel aluminum. And this is the MR output at room temperature 82%, and RA value is 40 MgO square micron. And when we measure this at 10 Kelvin, this one becomes 280. Very large value for CPP-GMR. So we look at the interface is beautiful, and this one is L10 model. But with the hard stem image, we cannot confirm whether or not nickel aluminum is there. So we did the EDS analysis, and we confirmed that nickel aluminum remains at the interface. So this one appears to be working, but we do not understand the detailed mechanism of large MR output at this moment. But this is the summary. This is MR ratio, and this is the year of the development. And many groups participate in this kind of effort, and STAR shows our contribution. And we have been updating the MR output using new materials and modifying the interface. And I said we need devices within this area. And currently, many of the CPP-GMR devices can satisfy the requirement for 2 terabit per square inch record. So I wonder if the low resistance MR devices has application only as a reader. So let's look at STT-MRAM application. And current STT-MRAM is, as you know, it's perpendicular device. The direction of the magnetization is perpendicular to the plane. And this size have to be reduced to 10 nanometer or so. So this is the MR ratio and RA requirement. So currently, the capacity of STT-MRAM is very small. So current TMR device can satisfy that requirement. But if we want to go to 5 gigabit or 10 gigabit capacity, large capacity STT-MRAM, the requirement for the magnetoresistive devices changes. As we saw in the CPP-GMR, we have to go to lower RA range, not as low as required for the CPP-GMR, but we have to definitely have to go to 1 ohm square micron range. And also, in order to make this to 10 nanometer thermally stable device, we have to use the material with high magnetocrystalline anisotropy energy, just like iron platinum recording media. And we need low magnetization to reduce the switching current by STT switching. And we would need low damping. And for the tunneling barrier, we need to reduce the RA value, so we have to use different type of barriers. So we may have the same problem for the STT-MRAM application. So this is the summary of all type of MR devices. Not only CPP-GMR, I include the data for the magnetic tunneling junction, TMR devices. MR, and this is the RA range. So now using Heusler alloy, CPP-GMR can satisfy this area. So this one satisfies the requirement for the 2 terabit per square inch recording reader. And as I said, if we are to achieve 10 nanometer node STT-MRAM, the required MR ratio and RF will be around here. So this one shows no MR device can satisfy this requirement. There would be two approaches. One is to reduce the band gap of the barrier of magnetic tunneling junctions. I call this as TMR approach. Change the spacer material ferromagnetic alloys to obtain high MR at low array range. Another approach is CPP-GMR approach. As I have demonstrated, we use half metallic material with large data and good matching, good materials combination between spacer and ferromagnetic layer. Then we may be able to go to this area. And one attempt we have done recently is, for example, to the MgO barrier, we give some doping. In the case of MgO barrier, this is MgO, and in order to reduce RA barrier, we have to decrease the thickness of MgO barrier. So currently, to this range, 0.3 ohm square micron, the thickness is 4 atomic layer MgO. And if we go to this thickness, reliability issue appears. Because unlike read head, in the case of STT-MRAM application, all the cells have to be reliable. And if we make the barrier thickness so thin, we get all kinds of defects. So one approach is to tune the band gap by doping doping metallic element. And one material we propose is a magnesium titanium oxide. The reason is we have been developing iron platinum media, and as I told you, we use MgO and barrier. MgO has a very poor wettability with ferromagnetic metal, so their contact angle becomes very large. But if we use doped titanium, this contact angle becomes small. That means the wettability becomes very good. So this is the actual result. This is TMR value. This is RA value. When you use MgO barrier down to 20 ohm square micron, MgO barrier is better than MgO. But below 20 ohm square micron, this TMR value substantially degrades. On the other hand, if we use MTO with titanium dopant, the degradation of MR towards low RA value is moderate. So at low RA range, we can get better result using MTO. The reason is, in the case of MgO, because of poor wettability, we get a lot of defects. We still do not specify what kind of defect, but pinhole-like defect. But in the case of MTO, very smooth interface without any defect. So by doing this, we can get high MR in low array range. And another attempt is to use totally different material instead of MgO. The band gap of MgO is 7.8 electron volt, but this semiconductor, CIGS, is copper indium gallium selenide. And this semiconductor is used as solar cell material. So in this case, we can grow nice compound semiconductor on top of ferromagnetic Heusler layer. And in many compound semiconductors do not show such nice crystallinity. But in this case, we get a very nice junction. And with 0.25 RA resistance area product, we get 43% of MR ratio, which is pretty promising. And this could be promising as a lead sensor because we apply the voltage to the device. That means we apply current. Then we get 22 millivolt of output. For the lead sensor, we need 12 millivolt of output. So this is almost 2 times larger than required work. So it's pretty interesting development. So for this, we were motivated to develop a lead sensor for the hard disk drive. But we are getting very large MR output. So we may be able to extend this application to other area. I'm not sure, but this is just a possibility. But definitely as a sensor, because for the sensor application, low power devices are needed. So with this, I want to conclude my talk. I just want to acknowledge those who contributed this talk. So Dr. Sakuraba, Takahashi, and Furubayashi, Kasai-san, Nakatani-san, and these are the postdoc, and also graduate students from the University of Tsukuba, because we have a program with University of Tsukuba, and students join university and do thesis research with us. So finally, I have 8 more minutes, so let me introduce where I am from. So my workplace is the National Institute for Material Science. This is the main building. And we are located in Tsukuba, 50 kilometers away from Narita and Tokyo. The access is very good. And if you are interested in, please do stop by. And this institute covers 7 major areas like functional materials, green materials, and nanomaterials, and characterization, and magnetic materials, that means us, and structure materials, and materials informatics. And in here we have a research center for magnetic and spintronics material. We cover all type of magnetic materials, including spintronics materials. So we are working on materials required for magnetic recording. We believe that there's bright future in magnetic recording. And spintronics devices, as I introduced you today, and we have large activity in the development of permanent magnet. And as you saw in my today's talk, we always look at structure very carefully because transport properties, magnetic properties are very sensitive to the structure of the devices and materials. So these are the staff members and group. And there are currently 12 staff members. And this is the group picture taken this spring. And finally, this is what I wanted to show. We have various internship programs, and if you're interested in, you can apply and come to our lab and stay for 2-3 months. And if you like, you can apply to the graduate program too. So thank you very much for your attention.
Question or comment? So the superparamagnetic size limit for L10 iron platinum is 2.5 to 3 nanometers.
Right.
But till now, experimentally, we have never observed nanoparticles or grains of that size. So what do you think the limitation is?
Yeah, that is definitely current issue. So the smallest size we achieved with iron platinum carbon is currently 6 nanometer. And there is a size limit for all that as well. So when we try to reduce the size, there's a thermodynamical reason that the L1 phase become unstable. So we cannot go so small to 2.5. But it would depend on the shape too. 2.5 means the diameter of the columnar side. So it would be different from spherical shape. So we do not know, but experimentally we know that if we try to reduce the grain size too small, they do not order the L1 cell structure. You're right. But 2 terabit per square inch is okay. I know that Japanese students are shy and quiet, but I didn't expect the same for the international students.
はい、Thank you very much. That's good. We have a coffee break time.